Hello and welcome to this next video. This is the third video in the series of Python decorators. First two videos, if you haven't watched it, I would recommend go ahead and watch it before watching this video. In this video, we are going to cover some special decorators that Python offers to us as Python programmers. So there are some special decorators, for example, wraps, cache, LRU cache. We are going to see all those in this video. Well, you can ask that why do we want to look at these special decorators? Why, if we can just learn decorators, how they work, and then probably we can walk away. But my answer to that would be you should always learn what is by default offered by Python as a from its standard library. Reason is that you may end up implementing such things which are already offered, and also knowing that doesn't harm it. It will only add knowledge to your and also it will add tools. It will make you feel empowered. So whenever you are working on very large Python based code bases or Python repositories, you will always see that these decorators that we are going to discuss today in this video you'll see that being used often. So it's really good to know that. However, let's get started. So the first decorators that we are going to talk about is actually called as wraps. It's available in its functools library in Python. So let's before we actually get onto the wraps decorator, let's see a couple of things that I would like to showcase here from the example. So we have this divide function. This divide function does nothing except to integer and does the division and returns a floating point number. We are actually doing that. We are not doing integer based division. You can do it like this. However, this function returns the floating point. So I will run it and show it to you. So if you see whatever it returns, I'm printing. I'm calling this divide int function, and I'm passing 150. So which is I'm returning 100 by 50 here, and it's returning 2.0. However, if I do this, it will return 2. It will return integer, but that's okay. That's not relevant here. Let us make it. If we don't want to lose precision, I think we should do it like this. But what I want to get to is that if this is the divide int function. Let me print one thing. So divide int dot underscore name. So what do you think should get printed? I think that was pretty straightforward to guess. Yes, divide int is actually a function object, and the name property, the underscore name would actually contain the name of that function. And let me print divide int. Let me print this. So you see this doc, this dunder doc property, it actually contains whatever you have. It actually contains the doc string that you have given to that function, which is actually here. So if you don't give this thing, dunder doc will be none. So it prints none. Let me include that here again. And if you print this, this will be the dunder doc string that you have provided. Well, it's fine till now. But in addition to this, actually, I'm trying to what I'm trying to do is I want to decorate this method with this decorator sanitize, which I have defined just above. What this sanitize decorator does is it has input validator, which actually validates the input that we are giving to that division function. For example, we know that division by 0 is not allowed. So it will actually validate that. And if we are trying to divide by 0, it will actually raise the error, raise the exception. So and also because we are expecting both the values and both the inputs as integer, this is just another check that I'm adding. So it actually checks if both the numbers, which is num1 and num2, if they both are integer, if any one of them is not integer, I'm saying that if it's int and it is int and not of the entire thing, if any one of them is not integer, it will again raise an exception that okay, probably one of the parameters that you are providing is not an integer, and later it checks for 0. If the second number is 0, it raises this error. Just before I forget, there are better ways to do this. You don't have to implement a decorator just to validate inputs for a division function. But what I'm trying to get to is that this is very easy example to understand the scenario that I'm trying to convey. So uh, coming back to this function, coming back here, um, if I just sanitize it, what it will do is it will check num1, num2, validate here in the input validator, and raise exception as based on the input that we are providing, right? However, we are not interested in that part of input validation, but let's see what happens if we decorate this divide int method with this sanitized decorator and see what are the values of these two things. Well, it got changed. As you saw previously, we had printed divide int. Now that is replaced with input validator, and next we printed dunder doc. Earlier it was, this is the divide function, which was coming from here, but now this function is input validator. I think now it is coming from here. This is the input. This function is input validator, performs validation on input. Well, why is that happening? um, it will be easy to understand, because we know that whenever we decorate a method, then decorator replaces our original function with the inner function, that with another function, which is here. It will replace with input validator function, which means our original function divide int will actually get replaced with this input validator function, just because we are decorating it with sanitize. So it's okay. It's not a big deal that we are having name and doc wrongly represented here as input validator and wrong doc string. But however, it is still is a misrepresentation of it. So most of the times, uh, we want to correct it. We want to, if at all you have to peek into the name property, you will always find that your divide int is actually pointing to the new function that is replacing it, rather the actual function itself. So this is where the wraps decorator comes into the play. So it is available in the func tools library. So you can do this from func tools import wraps. And what you can do here is you can just decorate this input validator function with wraps and pass func to it. Now what happens? This wraps has taken this function func. What is this function func? This is our original function, this divide int. It is actually this divide int method that is getting passed to this sanitize function as func, and wrap actually takes it as a parameter. Just before you get confused here, we have not seen any decorators till now which accepts any kind of parameter or argument. So you don't need to worry about this. We are going to cover it in like next video, or probably next video after that. So that's okay. For now, just understand that the wraps decorators can also take arguments. They can also accept parameters. So we are passing function as an argument. Wrap is accepting this function as a parameter. And now what happens? We are indeed decorating this input validator function with wraps, which takes this function as a parameter. What wraps does is wraps actually copies the name property and dunder name property and dunder doc property to the input validators uh, dunder name and dunder doc property, which means it copies the func, which is our original functions dunder name and dunder doc property, to the dunder name and dunder doc property respectively of input validator function. we know that our input validator function in our original function is no matter what, it is going to refer to this input validator function. We cannot change that, but however we can avoid this misrepresentation here, and we can copy the name and doc properties from our original function to the input validator function, and that's going to help us. So let's say we have sanitized it, because we sanitized we decorated it with this sanitized decorator, and we were getting this. Let me clear this out and run it again, and now you see that it is actually printing the uh, desired function name and the desired doc string. So that's what the wraps function does, wraps decorator does. There's one more thing that I would like to improvise here. um, in my previous video, when I was explaining decorator, I told that your the new function that is actually going to replace your original function, your decorator, is actually going to replace your original function with the new function, right? And that new function here is input validator in our case. And I said that your new function and your original function should accept the same number of arguments, and they should return the same result. Well, result part still holds true, but in case of arguments, you can actually improvise it. You can make use of the uh, star args, or like that variable number of arguments, positional arguments. You can make use of it, so that you can actually make this decorator available for other functions that accept different kinds of arguments, like different number of arguments. For example, you have this divide int here, and this divide int actually uh, takes only two positional arguments. Let's say that you have another function uh, which uh, which which adds three numbers, which means you are going to have three numbers, three positional arguments. And if you want to apply same kind of validator on it, so you have to decorate it with the same decorator. But it won't work, just because earlier we had this inner function that accepts only two positional arguments, but your other function, the add function, which is going to add three numbers, and is going to accept three positional arguments. So which means you will have to somehow adjust that. So what you can do is that, because we are only dealing with positional arguments right now, we are not dealing with keyword arguments. So what we can do is that we can replace it with args. It will work in both of your cases. Well, we have made this change. So let me add one more check. Let's say if length of args is actually 0, then I raise, or length of args is actually less than 2, raise a value error again, and I can say that number insufficient. Something like this. I'm just raising this. And this num1, you can refer to it like this, 0. And num2, you can refer to it like this, args of 1. And num2 again, args of 1. And args of 0. And then, or actually you can send it similarly, star args. So I hope you shouldn't see any difference in your output. So that's fine. It works. It works. So now what we have done is that we have improved our decorator in two ways, essentially. We have introduced this wraps, which actually replaces your new functions dunder name and dunder doc property with the original functions dunder name and dunder doc property. It replaces that, overwrites it. And now we have improvised it the way we are taking the arguments. We are now taking variable number of arguments, positional arguments, and that's how we are computing, so that it can be used with the now this function. If you had now consider this, you have this func which points to your int divide int function, original function. It takes two positional arguments, and if you pass it, it's valid. Now, if you had another function, let's say which took three positional arguments, like the add function I said, if you pass this as it is, that would work as well. So that's what we wanted to handle, and that's what we have handled here. So that's fine. And I hope you would have understood why wraps would be used. But mm, you can always make use of it if at all you want. You think that you have to make use of dunder name and dunder doc properties. If you have to at all look into it for documentation purpose, or just for name, you have to look into it. You can always go through this wraps decorator. The next in the list is actually very widely used decorator, and you would see it being used which is by default offered by Python, and it's being used all over. So the next decorator, what I'm talking about, is actually the cache decorator. Uh, to explain this, come let me show this example. This is our classic nth Fibonacci example. This is the recursive solution. This function also computes the nth number in the Fibonacci sequence. Okay. Now, let me show if what happens if we don't use cache. And let me just call it 5 or 10. So we want to find 10th number in the Fibonacci sequence. We are passing 10 to it, and then we are going to print result in the end. Whatever the result is, just let me, I have introduced this print statement here, which is actually whenever this nth Fibonacci sequence function will be hit, this print statement is going to be printed for that particular value of n. So we want to see and how many times this n is getting called. So let me clear this and hit this example. So we see too many. Yes. So if you see this, so many number of times 0, 1, 2, 0, 1, 2, 0, 1, 2, 6, 5, 4. There are repetitive calls to this nth Fibonacci sequence number, right? And 10 is hit here. 10, 9, 8, 7, 6. So I would, what I'm trying to convey is you could it's very obvious to look at that n equals to 2, it was hit here, n equals to 2 was hit here, n equals to 2 was hit here, and so on and so forth. N equals to 2 was hit here, and multiple number of times. N equals to 2, 0, 1 were hit multiple number of times, and for 3, 4, so on and so forth, they were hit multiple number of times. However, if you decorate this function with cache, and now for same input, let me execute this function again. Well, if you see here, result remains same, but number of calls to that function have significantly reduced, which means we are only hitting that function or executing that function for n equals to 0 to till n equals to 10, like 11 number of times, including 0 only. We are not executing that function beyond that. Now, let me tell you what cache does for this. If you are aware of dynamic programming, it's a very classical paradigm for solving data structures and algorithm related problems. So dynamic programming implements memoization, which means if there is a function which is hit multiple times for the same value of input, what you can do essentially is you can store that in input, you can store the result for that particular input, and when the function is hit again, you can retrieve that answer from wherever you have stored. Let's say in some cache you have stored, in memory you have stored, you can retrieve it rather than computing the result again. So okay, if you didn't understand that, I'll repeat it for you again. What memoization means, if there is a function which is hit multiple number of times for a given input, what you can do, when it is hit for the first time, you compute the result and store that result in a memory, and when that function is hit again for the same input value, you don't have to compute the result again, rather you can fetch that result which was stored from the previous invocation, previous function execution. So that's what the cache does. It actually stores whenever, for example, if n equals to 2, value of n equals to 2 was computed, cache had actually stored it in a map. It actually is a map, and in that map, it for n equals to 2, it would have stored that result. Now, when n equals to 2, when nth Fibonacci a function is called for n equals to 2 again, then what cache would do, it will actually look into that map, that cache, and fetch that result. And rather than it will not go, rather than executing this function all over again. And it happens for all the inputs that we are expecting. So I hope that made sense. That's okay. That cache helps us. Okay, one more thing I think it's really important to tell here. If you haven't, if you don't cache, if you don't use memoization here, uh, I hope you would understand what is time complexity. The time complexity uh, of of a plain Fibonacci sequence, Fibonacci number, a recursive solution, it actually is order of 2 power n. But if you use cache, it's only order of n because you are caching it. You are only hitting that function n number of times, and every time you have that value computed, so you can fetch it. So that's the thing. So let me tell you another thing. It's okay that cache is helping us, but what if your function executes for a significant amount of time? It executes for a longer duration, and you are expecting a lot of values to be stored in the cache. Okay, if you're expecting that your cache to grow like very big in size, it may happen that in this case your cache, whatever this cache decorator, where the memory that it is using to store all your values, that memory, that particular cache which is stored in the memory can grow very long, and that's not good. So that's where we are arriving on another solution to this, which is actually using LRU cache. This is the example number 3. LRU cache actually allows you to set the maximum size of that map, that cache. Uh, so what you can do is that it actually accepts 2 parameters, LRU cache. Function remains same for your example, for your information. Function is same. I'm just changing the decorator here. You can LRU cache also is parameterized, so you don't have to worry about parameterized decorator yet. We are going to see it in future upcoming videos, but for now just understand what these variables, what these parameters, keyword arguments mean. So max size equals to 5 means that if at all your function is going to hit, if you're expecting that your function is going to run for significant amount of time, even though it's going to have like it, if you expect that okay, there may be a lot of keys that can be pushed on that stack, and your stack can grow, your in that map, and your map can grow, and the cache size can grow. If you can if you are limiting it with 5, which means there will be only 5 entries in your map, it will not grow beyond that. And the reason why it is called as LRU cache is because it uses cache eviction policies based on least recently used. LRU cache max size equals 5, you can set that. And then it accepts the second parameter as well, typed. I can explain this. It's very interesting to know that if you set this try typed equals to false. Now let's say, I can explain you this with an example. Let's say that your cache is expecting an entry with key equals to 10, 10 as an integer, which means you want to store an entry with key 10, but you are also expecting another key with value 10.0. 10.0 is actually floating point number, and 10 is actually integer. If you set this typed equals to false, then what Python does is it will only create one entry for both of them. But if you set this typed equals to true, then Python will create separate entries for both. So when do you use typed equals to true and typed equals to false? So it's really simple. If you anticipate that if the value of input is 10, if and 10 is going to lead me a different result than 10.0, then you should use typed equals to true, else you should use typed equals to false for optimization or better performance. So what I recommend is that you can always use LRU cache, except you can use cache too. You can use this cache decorator too, but use it only if you anticipate that your function is not going to execute for very long, significant amount of time, and you don't anticipate that it is going to overrun your memory. However, let's see this LRU cache. Uh, as we have understood that your cache size is not going to grow beyond 5, and typed equals to false means what? Uh, let's run this as well and see what happens. Okay, I have run it for n equals to 100, and if you see, it was hit only for 101 amount of 101 times. There are no repetitive entries from 0 till 100. There are no repetitive entries. You can check that. So that's okay. If you, there is one interesting thing that I would like to show. So if you want to know the information about the cache, you can do that. So what you have to do is that this is the function that you're decorating, right? So the cache will be built against this function. What LRU decorator also does is that it adds one interesting parameter which is called as cached info, interesting property that you can use. So nth Fibonacci dot cache info, and if you invoke this method, you will see here a very beautiful explanation. So there are hits, there are misses, there is max size, and there is current size. So you see this max size, right? Max size is only 5, which means it never grew beyond 5. And current size is also 5, which means this is the current size of your cache in the memory. And that's what we wanted. We didn't want it to grow beyond 5. If you don't give max size as 5, just an important thing to note, if you don't give max size as 5, by default its value is 128. Another thing, if you give it as none, that means that there is no limit on max size, and LRU cache will start behaving as the cache. It will deactivate that limiting the max size, limiting the size of that map or the cache. That particular feature will be turned off. It will be deactivated, and LRU cache will behave similarly, same as cache decorator. Now we have this nth Fibonacci. We have seen this. Now let me explain you each one of these. Hits I will explain, but let me explain misses first. What is misses? Misses is whenever you hit that function nth Fibonacci first time for some n equals to x. For example, let's say n equals to 2, your function is hit for the first time, which means there is no entry for n equals to 2 in your cache. What you will do is that, as I said before, you are going to compute the result and you are going to save that in the cache. Now, however, when it is hit for the first time, you're going to go and look up in the cache first. Because no one knows, okay, if there is entry already present in the cache. So it's going to look for 2, but there won't be any entry for n equals to 2. So you compute it, and you compute it, you store that result for n equal to 2, which means when you didn't find that n equals to 2 key in your cache, it was a cache miss. And that's why we see miss so many numbers, so many as 101. And it's very logical to figure out why it is 101, because we have computed n equals to 100 from 0 to n equals to 100. From 0 to n equals to 100, there are total 101 numbers, including 0. And it's really logical to think that for n equals to 1, it is going to hit for the first time. For n equals to 2, it is going to hit for the first time. And for n equals to any value, 17, 18, 19, this function is at least going to hit for the first time, where the number will for that particular number, the value wouldn't be computed and there will be a cache miss. And hence we are getting total till 100. From 0 to 100, there will be cache misses, which is very logical to compute, and there will be 101 cache misses. And cache hits, what does that mean? That means that once you have computed, for example, again taking that example of n equals to 2, for n equals to 2 you computed previously and you have stored it. Now let's say you have you're hitting for the second time for n equals to 2, your function is hit for the second time for n equals to 2, you're going to look up, you're doing a lookup in the cache and see if there n equals to 2 is present. This time it will be present, and that's where your cache hits actually gets incremented. So there will be a cache hit. You don't have to compute that result once again. You can simply use the value from the cache. Uh, because I have also printed it, printed here, let me show that this thing here as well. So this second, okay, let me clear that. Okay, now you see this. Max size is none. Okay, let me run it for the same input. Your max size is none, but your current size is 101. This is interesting. Because we have no limitation on the cache size, max number of times, the max distinct keys that we can have is 101, from 0 to 100. And that's what our cache has grown to. Our cache has grown to 101 entries. If we had used LIU cache like here, we could have restricted it to 5. Like in previous example, in this LRU cache example, we saw that we restricted it to 5, so our current size was 5, but here current size is 101. Similarly, we have same number of hits and misses, but max size here is none, which means we have no limitation on it. Okay, so with that, I hope that you were able to understand what is a cache decorator, what is LRU cache decorator, and what was RAPS decorator. I hope that it would have added to your knowledge. And if you have liked the video, please like, share, and subscribe. And I'll see you in the next one.